Hi everyone, welcome to today's webinar on the challenges and solutions of moving vision LLMs to the edge. My name is Ben Gomes. I'm an engineer here at Expedera, and I'll be walking you through the challenges that we're facing when we're trying to move these models to the edge and the different ways that you should approach trying to really optimize them for that placement. So the first thing is, let's talk about what we actually want to cover. So LLMs, everyone knows them as these are large language models, and the first question that naturally comes up is, why are we talking about them in this context? So we're going to cover the background on LLMs, the underlying technologies and growth, and then we're going to tie that back to how it applies to edge AI vision, which is what the real goal of this talk is meant to cover. There's substantial challenges in moving these models to the edge, and so we're going to need to go through all of those. And lastly, we're going to really focus on the different techniques for making these models fit on the edge in a way that's actually useful to the intended use case. And part of that is actually going to be Expedera's own Origin MPU, but there's quite a lot of things that can be done to accomplish this. So we said that where we're really focused is large language models, but language models may actually be a bit of a misnomer in this context. So large language models are originally designed for modeling human language. Human language, though, there's no correct pairing of sound and meaning. So there's no language that has gotten it exactly right of, well, this is the correct word that you're going to use for this application. And this means that when you take that concept and scale it back up to a more abstract level, what this means is that with language, we're dealing with a structured ordering and aggregation of arbitrary objects. And at this level, you start to realize that the solutions that you come up with to solve language problems are going to be versatile and generalizable for many other problems. In large language models today, we already are abstracting words away to be numerical vectors. This means that we no longer are dealing with actual words, we're dealing all with numbers, and it's only at the very end of all of the work that we're doing on these numbers do we convert it back to being the words that the user expects to see. And this flexibility where everything is arbitrary and what we choose to pump through the model is part of why LLMs have been so flexible and why they've been core to the boom of AI today. So video, images, audio, computer binaries, all of these have been modeled straight from the tools that were developed for LLMs. And even now we're seeing that many LLMs are multimodal. They can process all kinds of different data types all in the same model. And what this means is that when we're talking about large language models, we essentially are talking about two different concepts that we're going to merge into one conversation. The first is that we're going to talk about anything that was designed for language, regardless of whether or not it's applied to language today. And we're also going to talk about models that maybe weren't initially designed with language in mind, but are bringing in language due to the benefits that it can offer. And the benefits that you're looking for here are that LLMs, whether they were built for language or whether they incorporate language later, are really, really good at maintaining semantics. So when you need meaning to be carried over across what you're doing, LLMs are going to accomplish what you need. So let's take a look at where we're coming from with this. Large language model today is used in all kinds of different ways, and you can even see different people trying to redefine the space. They'll say, well, oh, there's a small language model, or this is large. To put this in context, back in 2017, when the first transformer model came out, the largest version came in at 215 parameters. Today, that would be considered an extremely small model. BERT, similarly, just a year later, that maxed out at 335 million parameters. And just like the transformer, that was truly massive by the standards of the time. So with this in mind, we're not going to worry too much about whether or not something is large according to what we think of today, because in 5 years it's likely to be the same thing, where there will be an entirely different context on what counts as large, and it's not material to how we interpret the benefits that we can gain from these models and these architectures. So as we said, like today, they're much, much bigger. GPT-4, Gemini Ultra, we're already talking about well over 1 trillion parameters, reputedly upwards of 1.7 trillion, whereas Gemini Nano, the smallest version of Google's Gemini, is already 1.8 billion, which is multiple times larger than what was considered big just a few years ago. Now, one of the reasons that these models are getting bigger and bigger and bigger is that they start to exhibit, quote, emergent abilities when you get large. These start to appear around 1 billion parameters, but they really take off once you're above 10 billion parameters. So emergent abilities, these mean that if you pump enough data through these, if you give these enough parameters, they eventually start to show features such as apparently reasoning or other things that we didn't expect to be demonstrated. Because remember, most of the most famous models that we're talking about were originally developed just to predict the next word in a sequence. That's all they were meant to do. But when you give them enough parameters, they start to actually show some kind of reasoning abilities. Now, as we said, the largest LLMs are cross-trained with image data these days, and this is going to be a big part of what we talk about in the rest of the presentation. So let's lay groundwork for what we're talking about. We said that transformers started in 2017. What does this mean? So the transformer architecture is fundamentally built around the attention mechanism, and we're going to talk about that a little bit later. Now, information is going to be carried through and kept available within the context window for every token being analyzed. When we're talking about words, tokens are normally done at the sub-word level. So this means that if you're dealing with a word like run, running would actually be 2 tokens because you've added on that ing. Now, that's going to become a little bit less relevant as we get over to the vision applications, but the main thing is that how you tokenize the data that you're going to pipe through is a decision on its own, and this is one of the main decision points that is still a challenge for vision LLMs, how you want to feed that data through. Once you've converted things to tokens, these tokens are just super large multi-dimensional vectors. You're going to do a lot of matrix math to feed that data through multiple math operations until you finally get to the end where you can then have a predictive output for what you're looking for. Massive weights are required here, and they're typically going to be located in the largest amounts in the attention heads and in the feed forward layers. So when people are talking about LLMs being really difficult to get onto the edge, one of the main things that they're talking about is going to be the gigabytes of weights that they need to keep in memory for running these models. So we said that attention is one of the main defining features of these models. This is showing like what that actually looks like in practice. Now, it's going to be realized as a scaled dot products of queries, keys, and values matrices. But every time that you're piping data through these, you're going to need to do all of this math all over again, and it needs to be done for every token plus every token that's come before. So this means that the compute requirements as you're going through these attention heads is going to scale quadratically. This is the second major impediment for moving these to the edge. You have those huge weights that you need to deal with, and you have compute that gets very expensive very fast. Now, there's all kinds of ways to try to optimize this. One of the big ones, as you can see, the equation above the diagram there, we've got softmax, and we are using all of our three matrices, but you'll notice that there's a transform on that keys matrix, on the keys matrix. If you structure your data just right, or if you know what you're doing with your hardware implementation, you can actually avoid doing that transform. And that's one of the things that, for example, Expedera tries to make sure that we can do, make sure the data is coming through to these equations in a way where you need to do the least amount of additional work. So we've got transformers that we've been talking about, and there's also non-transformer vision LLM models. So for transformers, the first thing that is going to come up always are the multimodal models. So there's the big ones like Gemini and GPT-4. These are ones that are designed to run on servers with a ton of compute power available to them, and they are ones that, at least by the technology of today, are not ready to be moved to the edge. There's smaller ones, however, that often get used either on their own or as part of a larger complex, and this would be models such as CLIP. And what these do is they pair language to image. You could use CLIP, for example, just like AlexNet or ResNet, where all that it does is it tells you the object that it's identified in the image. Or you can then take that multimodal model, you can take CLIP and put it into a larger model such as Stable Diffusion, DALL-E, or Imagen, where they use CLIP to develop the latent space that then controls how a UNet convolutional neural network works to generate images. And when we talk about those, the first thing that you might think of is that, okay, well, do we really need that? Because I don't care if my phone can generate an image of a puppy. What I really want is for it to be able to help me understand what I'm seeing in front of me. Now, these models are focused right now on producing new images, but one of the original utilities of this technology is in-painting. So this means that if your camera sees something that's partially obscured, it can guess what's behind the obscured area. So even when we're not talking about novel generation, you get the ability to have a better understanding of the space around you based on what your camera is seeing. Now, there's ongoing efforts to reduce the sizes of all of these, and we'll talk more about those as we go. But the main thing to realize is that there's all kinds of applications here, and the challenge is figuring out how can we get the right size model onto the edge to fulfill the use case that we need. Now, there's also non-transformer models. The one I like to talk about is Dynalang. This is a model that came out of UC Berkeley. It's the most recent in the development of a line of models called Dreamer. And what this does is you have three models that are jointly trained in language and vision. And what they do is they work together to interpret the world. So the reason that this is so interesting and exciting is that you can see that as the agent is moving around inside these virtual spaces, it's narrating what it sees. And that narration, in addition to being a sense, sort of lossy, abstracted memory, it also serves as the basis for allowing better reasoning in what it needs to accomplish and how to accomplish that. And this application, whether it's from a non-transformer model or in a transformer model, is a key reason that you may want to use an LLM on the edge. It's that you can use it for self-driving or embodied agent purposes, and you don't need to worry about an internet uplink, and you don't need to worry about the latency that can come with that uplink. Everything's local, everything's controlled in your defined space, and therefore you're able to accomplish your goal with minimal additional risks. So as we said, these embodied agents, it's a huge area for these models to go to the edge. And the ability to have a language-based abstraction of what you see to be the way that you record or remember visual inputs means that you can end up handling way less data than you would have originally. So not only is it an effective way for making sure that your agent can interact well with the world around it and not get hung up because, well, this trash can's blue instead of red or something small like that, it also helps with making sure that you don't need to overbuild your solution at the edge. Now, these also get used a lot for observed events. We've seen, for example, that Gemini, even though that's a server solution, like it's hosted in the cloud, we've seen that it's been able to, for example, pick out when in a movie someone pulled out a piece of paper, what that piece of paper said. And this kind of video review and analysis, especially as the models continue to get better, is something that we expect to see pushed all the way out to the edge. Similarly, you can see that in satellite image review, when you're talking about physicians reviewing medical imaging, if you're driving your car and your car is helping you understand where there are hazards, all of these are things that these vision LLMs are very good at. Similarly, you can use them to identify information that you should care about from security footage. Now, the reason that you really want to do this, and something that I want to highlight it specifically, is that if I put up a video camera somewhere and it's recording everything that goes by, most of the time, I don't want that data. I don't want to know about all the people walking home from the elementary school that's 2 blocks away. I don't want to have any of that concern. I just want to know if there's a fight breaking out in front of my establishment. These kinds of solutions, you can put that data immediately into a vision LLM, and it will process the data and immediately determine whether or not there's an alert without you ever looking at or storing the footage. It is purely based on what you need to know and preventing you from gaining data that you would really rather not have the risk of possessing. So we talked a little bit about Dynalang and how you gain these abilities by putting language in context with vision. And this is that same kind of idea, but applied directly to self-driving and done as a transformer model. So Lingo 2 is something that came out this year. It's pretty exciting for us because it shows exactly where we thought the industry was going to be going. And what Lingo 2 does is you take your video input and it goes into a vision model that is eventually going to feed into a language model. Now, on the bottom right hand of our screen there, you can see that there's this video where the car is navigating the streets of London, and at every point it's narrating what it's trying to do. It recognizes what the hazards in the road are, what the situation is, and it's saying what it's trying to accomplish. That's not just a tech demo. That's not proving like, well, I can narrate what's going on. That text is then being used to predict what an appropriate driving action should be. So we were just talking about how text and language can be an abstraction and a lossy way of remembering visual data. Here, you have your visual data, it gets put in, but text is what's being used as the way to interpret what an appropriate and safe action to take should be. And that's where it predicts what the correct driving action is, and that's how this car is navigating the streets of London. So I've talked about all of the good things that can come when we push these models to the edge, but it's not easy. LLMs are compute and memory intensive, and as they get more capable, that is normally coming with more parameters. And you should always think of parameters as a proxy for the data and processing requirements, especially the data requirements. So LLMs to this point have been primarily cloud-centric. There's ongoing efforts to move them to the edge, regardless of whether or not we're talking about vision LLMs or conventional language-focused ones. but even ones designed for the edge have run into problems. Recently, there were 7 billion parameter models that were intended to roll out on consumer cell phones, and those plans had to get scaled back substantially just because even planned to be used on a cell phone, they were too resource intensive to allow the phone to be a pleasant experience with everything else that the phone needed to do. So this is an ongoing challenge where we are trying to get all of these models to the edge in a way that is actually appropriate and user friendly. Now, vision LLMs in particular need to be on the edge. We've talked about how these LLMs often are hosted in servers, but the use cases for vision LLMs specifically say, like, if you want to have your car drive without you touching the steering wheel, you don't want that to have a hiccup because your cell phone lost connection. You don't want to rely on the fact that maybe there's 30 other cars around you and the bandwidth is clogged. You need to know that your safety is being handled on site with minimum latency. And this is true for most of the applications on the edge. You can't afford to wait, and if you can afford to wait, it often still comes with the caveat that you would really rather not your data being sent over the airwaves. So how do we get them to the edge? There's 3 areas that these models are going to be optimized, and I break these down to model architectures, system resource utilization, and dedicated hardware support. So you can think of this as, what's the model that we designed? How do we implement it in software? And how do we implement it in hardware? So already there's substantial attention paid to alternative architectures. Especially interesting area right now are SSM models. So these would be models such as Mamba, Striped Hyena, and Hungry Hippo modules. Some of these are intended to just drop in as one-for-one replacements for the transformer blocks of existing modules. Some of them are intended to be trained up from scratch. Now, all of these have trade-offs, but we can already see that one of the main areas going forward as people try to get models with these abilities to the edge is that there's an open question of whether or not transformer is where we're going to stay. And so if you're trying to optimize for the edge, something that doesn't incur all of those high costs of transformers is absolutely someplace that people are going to continue looking. And as we said, with Dynalink, that's not a transformer module, but it's not a transformer model, but it reaps the same benefits that you expect from that co-development with language. The other thing that we see is if you don't cut the transformer modules from your model, maybe you can change where and how they're used. So Stable Diffusion XL famously reduced the number of transformer modules and changed where they were located in the model, saying these are still important, but we want to limit where and how we have to use them in order to get better results on inference. And then the last option that I want to call out when it comes to model architectures is distilled models. Distilled models essentially train a much smaller model off of a large one, and that smaller model, instead of trying to understand the data itself as we would think, instead it's trying to imagine how the larger model would respond to that data. So you can get very competitive accuracy despite being way smaller if you train a big model and then you use it as the foundation to create a distilled model. So let's move on to our second category. These are going to be system resource utilization optimizations. So the first and most obvious one is quantization. Most of these models are being trained in floating point 16, and you can go much smaller. The common target right now is to go down to int 8 or int 4, and what you're doing there is you're reducing the compute complexity and you're reducing the memory demands of both the model weights and the data that you're sending through it. The trade-off is that you're going to be taking a hit on your accuracy. There's all kinds of strategies and approaches to make this quantization process be less problematic for accuracy, but there is a price to be paid there, no matter how small. Other options that we see are that there are attempts in software to change the way that we feed these models through the processors. Flash attention is very common for most of the models these days, where it tiles the way that you send your model through the processor. So you get to use it at the highest efficiency that you can manage from software. And then the last one that I want to highlight is speculative decoding, where instead of trying to just process the data that you have in front of you, you're also going to guess what data is going to come down the way. So if you are able to correctly guess what additional data you're going to need to work on, then you can save all of that extra time and quite a bit of compute. So this is most often used with language-focused models, where you can maybe guess 2 or 3 tokens out in front and save that additional compute and time of running those in sequence. But it applies equally to more vision-focused approaches. Now, the last one that I want to highlight is our third category. This is dedicated hardware support. Here at Expedera, given that we're a hardware IP company, this is what we really get excited about and what we focus on. And so there's going to be really 2 options that you have when you're trying to do hardware support. The first option is that you can have a standard kind of NPU or GPU. And this is the most common approach that's used these days. And what that means is that you just have a processor that's really, really good at running a lot of matrix ops through the processor. But what you're getting as you do that is you are getting very generalized support. So if you want to really reap the higher improvements when it comes to how much utilization you can achieve, how little power you can spend, all of these things, you start to look at bespoke processors. These are processors where they're made with an awareness of what their end purpose is going to be. So, and this is what Expedera really focuses on. We know that our processors are going to be used for neural networks, such as these large language models, and we are able to make sure that our processors are already ready for this application. So let's take a look at one of the common problems for these models. And this is a problem that you can see really in most neural networks as we continue to reduce the number of parameters on a layer by layer basis to reduce the amount of weights that we need to handle. And as we try to optimize in every different way, we start to see a very specific kind of problem come up. So we're going to use Stable Diffusion 1.5 as our little guinea pig to show the concept, but this is going to be true across many kinds of models, and it'll just manifest slightly differently in each one. So Stable Diffusion is a well-known image generator. So the way that it works is you have a clip encoder on the front end, you take in your text, and you can use that to generate a latent that will be used to condition the generation of an image from random noise. Now, Stable Diffusion 1.5, this is a pretty old model. And when I say old, I mean a couple years. It's not that long ago. But it has 865 million parameters inside that denoising UNet that we see in the center of the screen. And actually accomplishing what that unit needs to do is about 750 billion operations that need to be done by the processor. So let's take a look at what that actually means. So on the left, we can see what the UNet actually looks like, and this is why it's called a UNet. We can see that on the left of the U, that's our starting input, and we feed it through, and all the way down, we're repeatedly downsampling it. with everything else that we do, it just gets smaller and smaller and smaller until we get down to the bottom. When we get to the right-hand side of the U, as we're going back up, we're repeatedly upsampling, but at every point along the way, we're bringing over those residual connections. So we're feeding back in the data that we had set aside as we downsampled and as we had done our other operations. Now, the interesting problem for this is if you look at the top graph there, that shows the parameters. So where are we spending our memory budget? There's a ton of memory demands on the layers in the center of the U, so think of as we get lower and lower. But where we're spending our compute budget doesn't align with that at all. Instead, we've got a heavy compute demand at the two ends of the U, but not so much in the center. And so when you're talking about these kinds of bespoke solutions where there's an awareness of the purpose that the processor is going to be used for, you're able to focus on right-sizing the system resources to make sure that you have all of that additional memory at the center, you have all that additional compute at the edges, but you're not just raising the levels up as high as they can go to be able to handle those peaks. Instead, you can do all kinds of operations to optimize both where you have your resources available or perhaps reusing excess resources that you have in order to take the burden off of the overtaxed resources. And this is the kind of thing that Expedera is very focused on, because the best way to accomplish this is in hardware, and it's where we really focus our efforts. Before we get to the end, I want to tell you a little bit more about Expedera's MPU, which has a role to play in how we bring these models to the edge. Expedera designs and licenses semiconductor IP, specifically edge inference engines or MPUs. Unlike other MPUs which you might see, Expedera's Origin MPU is a purpose-built AI inference engine. The core distinction of our technology is something that we call packets. Packets are very small, bundled segments which traverse the vertical path of neural networks. We essentially break down the layer computations so that these small bundles of data, including the required dependencies, can traverse the entire defined vertical of the network. This allows us, without changing the accuracy or math behind the neural network, to solve these neural networks in a manner that is more processor, memory, and power efficient. Particularly noteworthy here is that this extended routing of packets through the network allows us to minimize I/O operations, meaning that we directly address the feature that typically dominates the power and latency costs of neural network inference. Our Origin MPU with this technology is thus more power efficient, area efficient, and maintains a much higher utilization than other options available on the market, and thus has been the hardware optimization of choice for more than 10 million devices shipped by our customers. We have multiple smartphone, automotive, and consumer device licensees, and this broad spectrum of adoptees highlights the second core defining feature of our technology, namely that it is extremely scalable. Our single core scales from 3 gigaops up to 128 tops, meaning that in addition to supporting you today, our technology is already prepared to support you in the next generation or iteration of your product moving forward. We do this all while customizing the Origin MPU to fit our customers' needs and use cases, allowing these benefits to be had without incurring time-to-market risks for our customers. So, to conclude, the versatility of LLMs in handling and coordinating different types of data makes them an effective way of processing vision. This means that nearly all image generators right now are already built on LLM architecture, and we can see that embodied agents such as self-driving cars are incorporating LLM architecture in order to reap the benefits of the improved reasoning and the improved data processing that you can get from using this kind of approach. The path ahead for LLMs in vision is not uniformly transformer-based. There have been solutions that are both transformer and non-transformer, and as we go forward, we expect to see this diversity maintain. and perhaps expand. Now, transformers today are the lead in image generation, and non-transformer models are more competitive on embodied agents due to being less resource intensive and not needing to have quite the same use case requirements of transformers. Dedicated OEM support is going to be required to help make sure that these reach the edge at the most effective implementation. And we're going to continue seeing this support at all levels, but especially at the hardware level, where making sure that you can run these models in a way that is appropriate to your power availability and appropriate to the latency demands that your use case has. And Expedera in particular is really focused on making sure that this requirement is already met in the industry. So there's going to be a reference slide to follow. That's just to make sure that if you want to follow up on anything that we've talked about today, you've got the resources. And thank you very much for listening to this talk.